Welcome back to part B of our Cumulative 2 quick review. So I'm going to take you through the last 3 units that we have done so far. And again, this is called a quick review because the idea is that I'm just giving you some sort of quick tidbits or things to remember from the unit that you might want to pay attention to. And then after I've done that, I'll take you through some examples or select examples from the reviews themselves. All right, so the next unit that we're going to look at here is logical reasoning and set theory. So this was your purple unit. And in this unit, we were looking at puzzles and games. And so we've done that sort of throughout the semester, all sorts of types of games. Best thing I can suggest to you is to practice as many examples as you can. And then also on Google Classroom, there is a link with a whole bunch of different games that you can check out, like tic-tac-chess and Sudoku and Nonogram, Rush Hour, Mastermind, lots of different games. So just expose yourself to lots of strategy games so that when you encounter these problems, you can approach it from a strategic or a logical standpoint. All right, the other thing that we talked about in this unit was set theory, and we spent a lot of time working with Venn diagrams. We were also introduced to some new symbols. So if you look at this piece here that comes from your formula sheet, these are some of the symbols that we had. So we talked about sets and subsets, unions and intersections, and then we also talked about empty sets and complements. So if you remember, we often start off with sort of our universal set or a description of what a set might be. And then we got into talking about subsets. And so subsets are sets that fit inside the bigger set. For example, if I had a universal set that was defined as all of the numbers from 1 to 10, all of the even digits from 1 to 10 might be a subset of the union of the universal set. So we would have 2, 4, 6, 8, and 10. That would be a subset of the universal set because everything in set E fits into set U. So in order to say that something is a subset of something else, we have to know that everything in set E fits in set U. All right, so to be a subset, everything in the initial set has to fit into the bigger set. And remember that E can be a subset of itself, and the empty set is the subset of everything. And then we got into looking at Venn diagrams, and we talked about unions and intersections. So if I have two circles here and they are not touching each other, that means they're not overlapping, they would be called disjoint. If they overlap, however, that point or section where they do overlap would be called our intersection. So A and B would be that part right there. If we're looking at A union B or A or B, it would be everything in those circles. So if you remember, A or B means A or B or both. And of course, we got more complicated as we got into bigger diagrams. We were looking at 3 circles, and then we were looking at quite a few problems. And when we're looking at a word problem with a Venn diagram, if I know the value that's in the middle, let's say it's 4, and then I'm told that this section here, we'll label this A, B, C. If I am told that A or C represents 6, well, then I don't put a 6 here because that now would represent 6 plus 4, which is 10. Instead, what I would do is I would put a 2 here so that 4 plus 2 represents 6. If for A and B, I was told that A and B was 7, I wouldn't write a 7 in there. Instead, I would write a 3 so that 3 plus 4 would total to 7. And then we got into more complicated ones where sometimes we didn't know the middle value and we had to do some math to figure that out. Now, a lot of times it was the notation that was giving some trouble with set theory, and so we'll look at some of those as we go into some examples. All right, now something else that we're asked sometimes, the number of students in the universal set, that's another way to write that would be n bracket u. So the number of the elements in the universal set. So anytime you see an n bracket set, we're looking for the value of or the number of elements in that set. All right, moving on. Remember that we did a lot of work with shading diagrams. So it's important that you go back into your original notes to look at all of the different types of shading that we had. I'm going to take a look at the next example here. A lot of times we're given the description of sets and we have to actually start by writing out what those values are. So here we're told that set X is the factors of 16, set Y is the factors of 8, and set 7 is even numbers less than 10. So we start by listing all of our numbers. So all of the factors of 10 would be 1, 2, 4, and 8. And then all of our factors of 8 would be 1, 2, 4, 8. I also missed one up there. It should also have 16. So 1 and 16, 2 and 8, and 4 and 4. And then we've got 1, 2, 4, 8. And then even numbers less than 10. Well, this would be 0, 2, 4, 6, and 8. Now, we haven't been given specifics about how far down we go with even numbers, so I'm just going to start with 0, 2, 4, 6, 8. We don't include the 10 because it says less than 10. So we can set this up as a Venn diagram. We can also just look at the information that we're given here, and we're asked to identify the set A, X, or Y. So we'd be looking at things that are in X or Y or both. And so if you notice, we have 1 in both, 2 in both, 4, and 8. Then there's also a 16. So it'd be 1, 2, 4, 8, and 16. For the second question, we're asked how many elements are in X and Y and Z? Well, if we look at what's in common in all three, we have 2's that are in common, we have 4's that are in common, and we have 8's that are in common. So the number of elements in X and Y and Z would be 3. All right, sometimes we get a little bit trickier here. If we're looking at this one here, it says the number of elements for black and not F. So this would mean we're looking at the number of elements that are black and not face cards. And so we would look into our diagram there and we try to find all of the elements that are black and not a face card. Again, with some puzzles, it's important that you take a look at what the question's being asked and just break it down using whatever strategies you have been using up to this point. And so sometimes that might be guess and check, that might be looking for a pattern, that might be creating a table, but ultimately you're just trying to use common sense logic to figure out or pulling from previous knowledge to solve these problems. All right, moving on, we're going to practice drawing out a diagram here. And so for this one here, it says, during a Pepsi Cola taste test, the following information was gathered. 36 liked Pepsi, 55 liked Coca-Cola, 11 liked both, and 4 didn't like either. And the question is, how many people did the taste test? So we'd be looking at Pepsi, we'd be looking at Coca-Cola. So P for Pepsi, C for Coca-Cola. This would all be included in the universal set. And we know that 36 liked Pepsi and 55 liked Coke, 11 liked both. So we start off by putting our 11 in the center. And since 4 liked neither, that would be outside. Now, if 36 liked Pepsi, that includes those 11 people. So 36 take away 11 would be 25. And then Coca-Cola, 55 minus 11 would be 44. And then from there, we could go about answering the rest of the questions. Now, they often got a lot trickier when we got into working with 3 diagrams, and this might, or 3 circles, so this might be an example we could use. So number 7, a gaming company surveyed 51 customers as they left a local game store. From the survey found, we were given these pieces of information. So we're looking at Call of Duty, World of Warcraft, and Legend of Zelda. So I'm just going to draw my circles here and label them. And so we're looking at Call of Duty, World of Warcraft, and Legend of Zelda. And so first of all, we're told that 12 people purchased none of the games. So we would have 12 outside. 2 people purchased Call of Duty and Zelda, but not World of Warcraft. So Call of Duty and Zelda would be here, but not World of Warcraft means this number is 2. We're also being asked how many purchased all 3 games, so we know that the center will be X. 3 purchased World of Warcraft and Zelda, but not Call of Duty. So World of Warcraft and Zelda, but not Call of Duty would be 3. And then 5 purchased Call of Duty and World of Warcraft, but not Zelda. So this would be 5. Now, 15 people purchased The Legend of Zelda. So that means 15 take away these three elements here. So 15 take away 3 take away 2 would be 10. So 10 minus x. And then for Call of Duty, 12 people purchased. So 12 minus 7 would be 5. And then minus x. So 5 minus x. And then the last one, 28 people purchased World of Warcraft. So 28 minus 8 would be 20. We'd have 20 minus x. Now, in order to figure out what x is, we're just going to add up all of our elements. So if we go 5 plus 2 plus 3 plus 10 plus 20, we get 45. And then if we add up all our x's, we've got a negative x and a positive x, a negative x and a negative x. Another negative x has negative 3x plus x is negative 2x. And we also have to remember to add that 12. Okay, equals to the 51 people that were surveyed. So 12 plus 45 is 57. So we have 51 minus 57 would equal negative 6. So we start off here, we've got 57 minus 2x equals 51. Subtract 7 from both sides, and we have negative 6. Divide by negative 2, and we have 3 years. Or not 3 years, but 3 games. Okay. And then from there, we're asked how many people purchased the World of Warcraft only. Well, that would be 20 minus 3, which would be 17 people. All right, so that takes us through logic and set theory. That was a fairly short unit. It's really important that when you start looking at set notation, we had some examples of that in our previous reviews, but I didn't go through any here. If I was given a set, for example, where I was told set J such that J goes from negative, or that J equals maybe 2x, and x is greater than 0, greater than or equal to 0, and less than or equal to 5. Well, when we set up our set notation, that's what it would look like. But when we actually figure out our elements, we're going to have to take each of those elements from 0 to 5, substitute it into our equation, and that will give us our new elements. So for example, 2 times 0 would be 0. 1 times 2 would be 2. We're assuming that we're told that x is the element of natural numbers, or whole numbers in this case. And so 1 times 2 was 2, 2 times 2 is 4, 3 times 2 was 6, 4 times 2 is 8, and 5 times 2 is 10. And then that would be the set that we would actually be working with. All right, so moving on to permutations and combinations. This topic and the next one we just finished going through, so we probably don't need a ton of review on it, but we'll go through that anyway. Factorial notation, this is one that caused some confusion when we had to break things down. For example, if I had n minus or n plus 2 factorial divided by n minus 1 factorial, and I had to break that down. Let's do n plus 1 factorial, I had to break that down. Well, I would start by breaking down the top. So I'd have n plus 2 times n plus 1 factorial, and that would be over n plus 1 factorial. As soon as those disappeared, I'd be left with n plus 2. So quite often we had to break things down in order to get to the next step, either simplifying or solving. Then we got into talking about fundamental counting principle. Okay, so if I have maybe 3 choices for color for a bedroom, and then I've got 4 choices for furniture, and I've got 2 choices for arrangement, it would come up with 24 different possible bedrooms that I could have, 3 times 4 times 2. We got into talking about permutations and combinations, and we were also looking at different types of restrictions. So whenever you're doing any type of question that involves restrictions of any kind, that should be the first step, is to always deal with your restrictions first. When we're deciding between permutations and combinations, we have to ask ourselves, does order matter? And if order matters, then we're dealing with permutations. If order does not matter, then we're dealing with combinations. And it's important that you always take a look at your formula sheet to get the full formula. Quite often with multiple choice, you're not asked for the final answer, but instead you're asked for a step in the process. Now, some key words. If I'm looking for words that tell me something is a permutation, okay, we've got keywords like arrangement, or arranged. We're talking about order mattering. We might see something about an executive committee. We might see something about different prizes, okay, or different placings. And if we're talking about combinations, then we're looking at things where order does not matter. For example, a team or a group or a committee. We might be looking at words like select, okay, or group, okay? So anything where order does not matter would be combination. And then the last thing on your formula sheet, we have this n choose r can be written as n over r in brackets. All right, now with probability, we're looking at 4 specific formulas. These also come in handy when you're working with set theory and your Venn diagrams, but it's important that you know what each of these formulas represents. So the first one represents a situation where the items are, or the elements or the events are mutually exclusive. The next one is not mutually exclusive. Then we have independent and dependent. Now, quite often you're going to be asked questions where you're given some numbers and you're asked, is this mutually exclusive or is this independent? All you need to do is substitute the values into the correct equation and see if it makes the statement true. And if it does, then it meets that criteria. If it doesn't, then it doesn't. When we're talking about events that are mutually exclusive or not mutually exclusive, this means there's no overlap. So mutually exclusive events have 0 overlap. In other words, they can have no events in common. So for example, if I was rolling a die and my events were either getting odds or evens, well, there would be no overlap. It would be mutually exclusive because I either have odds or I have evens, but I can't have both. So mutually exclusive, no overlap. Not mutually exclusive would have an overlap. So when we're looking at our probability of A or B, it would be the probability of A plus the probability of B minus our overlap. And then when we get into independent and dependent, this has to do with whether one event impacts the other event. For example, if I had a deck of cards and I pulled out a card, I looked at it and I put it back in the deck, I haven't changed the number of cards in the deck and I haven't changed the number of outcomes that I have. And so it's independent. The outcome of one event has 0 impact on the outcome of the other. That's different than if I have a card, I pull it out, I keep it out, and then I pull again. That would be an example of a dependent event where the outcome of one event directly impacts the outcome of the other event. And so when we start looking at our formulas here, if it's independent, the probability of A and B is the probability of A times the probability of B. Now, if we're looking at dependent situations, then we have to deal with conditional probability. So the probability of A and B would be the probability of A times the probability of B given A. So the probability of B given that A has already occurred. All right, so let's take a look at some examples. So a number of these we actually talked about in class today, so I won't go through everything. There were quite a few people who asked about numerical response number 3. I'm trying to decide if this was a combination or a permutation. Well, when I'm calling to order a pizza, it doesn't matter whether I order ham and pepperoni or pepperoni and ham. It matters more that I'm getting ham and pepperoni on my pizza. Or for those Hawaiian fans out there, I know my husband's a Hawaiian fan, ham and pineapple. But if you ever talk to Mr. Ricci, you don't put the pineapple on the pizza. All right. And for me, it's always about the deluxe. I love lots of veggies and all that olives and everything on my pizza. All right. So when we're making a pizza here, this one's asking how many different pizzas can be made with 0 to 5 toppings. So that means 0 toppings or 1 topping or 2 or 3 or 4 or 5. So this would be 12 choices, choose 0, or so plus 12 choices, choose 1, or 12 choices choose 2, plus 12 choices, choose 3, plus 12 choose 4, plus 12 choose 5. And then that would be what we would actually be calculating. Looking for keywords, sometimes, like this question here, I would actually draw out a tree diagram to figure out what all of my outcomes are and then break that down there to see how many combinations I have. When we're dealing with words like conference, you always have to remember to divide by your repeats. So don't forget that if there's repeating letters, we need to divide them out when we're using factorial notation. And moving on here, if we're looking at committee, keyword there tells us it is a combination type question. Often when we get multiple choice questions, we have to ask ourselves, does order matter? Are we choosing and then arranging, or are we just putting it all together and arranging? Those are all important things to look at. And when you get a question like number 8, where we're asked which of the following will give the most area codes, you're going to actually have to figure each one out individually to see which one gives us the most codes. Questions, we had lots of questions about number 5 today. So assume that a handshake takes 6 seconds. About how long in minutes does it take for all 45 students to shake hands? Well, order doesn't matter when we're shaking hands. So we have 45 people shaking hands. Only 2 people can shake hands at a time. That's going to give you a certain number of handshakes. We're going to take those handshakes and multiply by 6 because it's 6 seconds per handshake. And then once we have that in seconds, we can convert it to minutes. Another question came up here about the quadrilaterals. Remember that if I have a circle and I'm creating quadrilaterals, that means I'm choosing 4 dots at a time. So I don't exactly know how many dots I start off with, but I know that in the end it's going to make 35 quadrilaterals. So it's going to be n choose 4, because there's quadrilateral has 4 sides. N choose 4 equals 35. All right, remember with pathway problems, we can do these one of 2 ways. If I'm actually figuring out this entire distance around or the entire set of pathways, I would count each side, east and south. So we got 1, 2, 3, 4, 5. So this would be 5 factorial. Down here would be 4 factorial. And we add those together. So we'd have 9 factorial divided by 5 factorial, 4 factorial. So we're treating these, the 5 and the 4 factorial, like repeating values because we're hitting those distances or those directions more than once. Remember, if we're ever asked to find out the number of ways that something cannot pass through, it's often easier to figure out how many ways it can pass through and then subtract from the total value. All right, when we get into probability here, we've got a question where we're told that the probability of a particular baseball team winning a game is 4 out of 5. We want to know the probability that the team will win their next 2 games. It's important that you use your probability notation. So we're asked about the probability of a win and a win. Well, if you remember, and in math means multiply, and the probability of getting a win is 4 out of 5. Since these are treated like independent events, we don't have to worry about any type of dependent or conditional probability. It's important when you're doing your probability questions that you read carefully as to whether something's included or not included, what your number values are, and then double check using the formulas if you need to. For number 19, this would be an example where you're given values and then you're asked how it fits with the properties that you know. And so if we want to find out if 2 things are mutually exclusive, if they're mutually exclusive, then the probability of A plus the probability of B would equal the probability of A or B. And so then we would go about checking to see if that's true. After we know that, then we can check to see if it's independent or dependent. If the value of A and B is 0, well, then we definitely know it's mutually exclusive, and then we can go about checking the rest of our formulas. For checking whether something is independent or dependent, we're looking at whether or not the probability of A times the probability of B represents the probability of A and B. Now, if you notice, we don't actually know what the probability of A and B is, so we would have to first plug it into our non-mutually exclusive formula, which would be the probability of A plus the probability of B minus the overlap. Now, if that overlap has any type of value, then we definitely, other than 0, then we definitely know that the value is not mutually exclusive, but then we would have to take our values for A and B and multiply them out to see if it's independent or dependent. Again, anytime we're working with words, make sure you check for your restrictions and check for any repeats. All right, quite often you're going to be making tree diagrams when we're solving these problems. So I'll take you through this question here. We've got a young basketball player practicing his free throw. The probability that he makes the first basket is 0.4. So the probability that he makes the basket is 0.4. And that means the probability that he misses the basket is 0.6. So the probability that he misses the basket is 0.6. Now it says each time he makes a basket, the probability that he makes the next basket increases by 15%. That means it'll now be 115% of the original amount, so we can multiply by 1.15. So we want to know the probability that he makes the second basket given that he made the first basket. And so if he makes the first basket be 0.4, we want to multiply by 1.15. And so 0.4 times 1.15 gives us 0.46. So then we're looking at the probability that he misses the second basket given that he made the first one. Well, that would be 1 minus 0.46, which would be 0.54. All right, let's take a look at the next question. We're told that each time he misses a basket, the probability that he misses the next basket increases by 25%, so 125%. So what's the probability that he misses the second basket given that he misses the first? Well, the probability that he misses given that he missed already. Well, that would be 0.6 times 1.25. So 0.6 times 1.25 is 0.75. So the probability that he makes the second given that he misses the first, well, makes the second given that he misses the first. And if we take a look at that, 1 minus 0.75 would be 0.25. Now, once you have that, then you can set up your full-on diagram. So you would have making a basket and not making a basket. And then we would have making a basket for the second one, not making the basket. And then we have making the basket and not making the basket. And so our probability is the probability of B1 and B2 would be 0.4 times 0.46. Which gives me 0.184. And we would go around or go down and fill in all of the rest until everything totaled to 1. And then we can use those values to solve the remaining questions. All right, guys, that is, again, a real quick run through of the last 3 units. You really can't get enough information just through that. It's really important that you do some practice questions and you ask for help. Make sure you have a good understanding of all of this before you go into your test later this week. All right, that's all for now. We'll see you again later. Bye-bye.